Yeah, this is the new kid on the block in terms of NASA's super observatories. We're going to start, however, by going back in time and talking just a little bit about the Hubble Space Telescope. And I don't know if any of you recognize this, but last August, we passed the point in time at which the Hubble Space Telescope has been in orbit for a third of a century. A third of a century. It's like a Timex watch. It takes a licking and keeps on kicking. And
wait a minute.
there we go. So this is what we're going to start by a quick review of the Hubble telescope, and then we're going to go on with the James Webb telescope and why it is so different and so much better in some ways. Hubble telescope launched in 1990. Importantly, had a main mirror that was about 8 feet across, which is even bigger than Mars, I think, but close. And it was importantly, it was put in an orbit. Let's see if I can get this cute thing to work here. It doesn't supposed to do that. Hang on.
Is your app running?
That should be. Well, all right, we'll just work with it. Importantly, it had an orbit that was only about 400 miles up. This will allowed it intentionally to be serviced by the various space shuttle crews, including the crew that's technology. And so it was named for Edwin Hubble, who was, made his claim early in the 1900s. Importantly, he proved that, well, you can see the ticked off there. At that time, we didn't realize that there was more than one galaxy. It was thought that distant places that we now know to be galaxies, like Andromeda, Whirlpool, and so forth, were just sort of outlying islands, just sort of on the fringes of our Milky Way. And it was Hubble who first realized, or actually he confirmed the fact that the Andromeda galaxy, for example, is actually very, very far away, much farther away than it could possibly be associated with the Milky Way. And then later realized that the universe was expanding. And this became very important because up until that time, we look out in the universe and we realize there's all this mass. And Einstein pondered this, and he wondered whether everything was going to come back together, or whether there was this sort of anti-gravity that was keeping things in place in space. He initially rejected that idea, but he turned out to be right. We know that today to be what we call dark energy. But in particular, Hubble discovered that the universe was expanding. And expanding in such a way that the farther something is from you, the faster it's moving away from you. Now, that's a little bit hard to understand, so I've reduced it to its most basic. Do you know how hard it was to find a YouTube video of a loaf of raisin bread rising? I found it. So imagine one of these raisins is the Milky Way, and all the other raisins are galaxies. So if you're in the Milky Way and there's another raisin right next to you, you're moving apart, but not very fast. Right? The whole loaf is expanding. On the other hand, a raisin on the far side of it, as it expands, is moving away from you at a much greater rate of speed. And that is, in essence, what the expansion of the universe is all about. And so Hubble's job was to try, one of its principal objectives was to determine what the exact expansion rate of the universe was. This was not well known. Part of the problem is that we can spectroscopically look at a distant galaxy and determine how fast it's moving away from us because of Doppler shift, but we don't know exactly how far away it is. And you need both of those to do this. So this was Hubble's job, and almost, Hubble had a lot of problems during its development. It was way over budget, way over timetable, and when it was finally launched, it was realized that the primary mirror, the essence of this telescope, was ground very precisely to the wrong shape. you know, on the scale of the width of a human hair. And this caused the light from the star, which should be kind of a pinpoint, to be smeared over a large area, what we call a point spread function. It didn't bring all of the light from a given star to a point as it should have. And so Hubble suffered from mushy stars, and NASA kind of was keeping this under wraps, but it soon became apparent that this was something they were going to have to deal with when they announced. And when they announced that Hubble had been incorrectly built, it did not go over well with the public opinion. And so the solution was pretty simple, which was on one of these servicing missions, fortunately Hubble was within reach, was to go up and place corrective optics on the existing experiments of the instruments, and then on all future instruments to build them with this sort of incorrect shape in mind. And so we got rid of the mushy stars, everything's great. Hubble became fantastically successful. It was visited by 5 servicing missions after its launch to do things like put in new instruments, replace batteries, replace the solar panels, polish the fender, that kind of stuff. And so it became very, very successful. The last, I should back up. The last servicing mission was in 2009, 14 years ago. And it's still working just okay. It's all the instruments are okay. It's a little glitchy here and there.
It's in shutdown mode right now.
Is it right now? Well, sorry to hear. Another glitch. But this is a kind of short list of all of the amazing things discovered. It did, in fact, confirm this expansion rate of the universe, what's become called the Hubble constant. Looked at giant black holes, looked at discovered protoplanetary disks, and even has some extrasolar planets. But Hubble had its limitations. It was essentially a regular optical telescope. It could focus light. Design, it and its instruments were designed to basically look at the visible slice of the electromagnetic spectrum, what we see every day, plus a little bit of ultraviolet, plus a tiny bit of the infrared spectrum. Not very much. And so it was recognized that there is every time we look at the universe in a different wavelength of light, we discover new things about it. Think of, for example, examining the universe in radio wavelengths. We discovered things at the edges of the universe, very energetic things, or in gamma rays. All of these different wavelengths play a role. So we hadn't really done a good job of studying infrared light. Infrared light is the light portion of the spectrum just beyond the red end of the visible light spectrum. Think of it as heat radiation. And there's the whole electromagnetic spectrum. Now, we have had in the past spacecraft that have studied infrared light. NASA itself had launched the Spitzer Space Telescope. The Europeans, by the way, I'm going to get off my soapbox here for just a second. NASA does not do it all. They would like you to believe that. There are major observatories, major planetary explorers, moon landers, Mars landers that are done by other countries other than NASA. And so, in particular in the infrared, the European Space Agency, which is a sort of consortium of European countries who pool their resources into one big space program, have done a really good job of studying the infrared, but with relatively small spacecraft. And so there was a need to go bigger. Why we want to do that is illustrated by your friendly meerkats and crocodile. This is what they look like in visible light, but this is what they look like in infrared light. The meerkats, because they're warm-blooded, are getting off the top, and the crocodiles are not. So you can learn more about the universe, or meerkats for that matter, by studying in the infrared. And so we can capture one of the biggest areas is the warm glow of dust. Now think of the interstellar cloud sitting out in space with no stars in it. It's black, but it's not absolutely cold. It gives off a little bit of heat, which can be detected. And so by detecting, by going out and looking at things in infrared light, we can see, not only we can see clouds that we can't see visibly, but we can peer into them, because the longer wavelengths of infrared allow us to peer into the dust in ways we couldn't before. So for example, this is the Eagle Nebula, very famous. In the middle is those three little fingers there, which came to be called the pillars of creation. You can see them there in visible light. But then when you start to look at them in the infrared light, you get to see things that you can't. And in particular, I want you to notice that in the middle panel, we're actually peering through the fingers of dust to see the stars that are beyond. So that's just an example of what we can do. Not only, there are all kinds of things like this, dusty objects nearby that we want to study in infrared light. But the other thing is really important is that infrared light allows us to peer farther into space than is possible in visible light. And this is what's going on. You can see there the infrared of the various parts of the spectrum, right? And it turns out that the farther we look, the more ancient the light we try to see, it gets shifted into the infrared. Now, you're probably familiar with this. This is called the Doppler effect. I want you to notice this happens to be with sound instead of light. But as the car is coming toward us, it'll have a higher pitch. And as it's moving away from us, it'll have a lower pitch. For standing in the road. Okay, and so what ends up happening now? Think back. The universe is expanding, and so as the far reaches of the universe, the visible universe, are expanding away from us, the light that those objects emit, maybe invisible light, maybe X-rays, maybe ultraviolet light, gets shifted, gets redshifted, to redder and redder wavelengths, until you reach a point that the objects you're trying to see are no longer visible at visible light. You have to look in the infrared in order to see, right? And so, I'm sorry, you don't believe me, I can tell. So, Lisa, get up here and pick somebody else to be up here with you.
Mario, hop up there, would you?
Okay, Mario.
All right, you hold that in. Mario, you can hold this in.
Kelly's gonna try and get under it backwards.
You know, there was a time. Okay. Come close to me. Closer to me. About here, Mario. No. Don't squeeze it. Just come. There you go. You come here. You can have one end. Oh, look, this is a standard issue slinky, and you can have the other hand. Okay. Stretch it out there. So, Lisa, if your right hand, I want you all to notice the wave, right? It's pretty consistent all the way across. This is a wavelength of light. As you approach me, slide your hand. What happens? The wavelengths get shorter. It becomes blue shifted. Mario, go the other way, please. As Mario moves away from me, those wavelengths become red shifted to longer and longer wavelengths. So what might have been a visible wavelength of light, say blue light, gets shifted beyond the reach of visible light, and we have to go into the infrared and see. Right? Didn't they do a great job? I think they did. Got it. Got it.
Should have asked Mario to fix Hubble.
Mario, if you put a GAAC sign on that pole, you could march in the Horribles parade.
Okay. So now, before we get to the actual nuts and bolts of the Webb Space Telescope, NASA's traditionally named its big observatories after famous astronomers. Hubble Telescope, Hubble, Chandra for Chandrasekhar, who was a high-energy astrophysicist. Lyman Spitzer was especially good in the infrared. So who is James Webb? Well, here's a hint. He was not a scientist. He was a career diplomat in the U.S. government, State Department, and others. But importantly, he was the NASA administrator during those crucial early years that led to the Apollo program, and importantly, like, that nobody really remembers, the real beginnings of NASA as a powerhouse in the development of what we now call space science. Learning things about the rest of the universe using spacecraft. And so it didn't start out being called the Webb Space Telescope. It was going to be the next generation. This idea actually was kicking around as late as the late 1990s. After Hubble had been launched, you know, people started thinking, well, what's next after Hubble? And it was going to be launched as soon as 2007. It was going to be always a kind of infrared telescope with a modest budget. Boy, were they wrong. It underwent a major redesign at one point in 2005, and so everything ballooned. The timeline ballooned, the cost ballooned, and even then, the launch was going to be in 2013. That was 10 years ago. That didn't happen. But you know, everything about this was larger, bigger, more technologically complex. And you can see there, this is the Webb telescope. Yes. Oh, thank you very much. The Webb telescope. Sorry. It's not doing what I wanted. Well, maybe it's the zooming of it. Anyway, on the right is the Webb telescope main mirror, its primary mirror, compared to Hubble's at the left, and the concept was so big that no rocket nose cone could contain it. So in order to create a main mirror this big, first of all, it had to be built in segments, and then those segments had to be able to be folded up, as you'll see here in a second. So this is three of those telescopes comparison. And so the final cost ended up being about $10 billion, a lot of money. And it was finally launched on Christmas Day in 2021. It's almost exactly 2 years ago. And this is, I just find this a great picture. This is some of the mirror segments, which are gold-plated beryllium. Beryllium is chosen because when it gets hot and cold, it doesn't expand or contract very much. So this allows the mirror to maintain its shape out in the coldest space. And this is nearly completion. You see all the mirror segments there, and this kind of shows it partially folded. So I had to fold up origami style to fit in the nose cone. And so the real key to its success, now we're talking about not collecting light, but essentially collecting heat. And there are a lot of sources of heat in in the space near Earth. We could never do this spacecraft in the same orbit that Hubble was in, because the ground below us on the Earth is a source of heat, even on the night side. And so the solution was to launch Hubble and launch the Webb telescope and have it very far away from the Earth. It's still in sunlight though. And so this 5-layer heat shield was developed to reject most of the sunlight. So here's what happens. Imagine the sunlight shining up from underneath. On that surface, on that first surface, there is a very high temperature. But because of the layers, by the time you get to the backside where the telescope is, you're actually within some tens of degrees of absolute zero. So it does a very good job of rejecting the heat from the sun and allows the delicate instruments to measure heat essentially from these distant sources that are up to 10 billion light years away. It's a multinational operation. The biggest players are of course NASA and the European Space Agency, the Canadians, but a lot of different countries got into the act. This is a kind of schematic. You can see the sun shield down there at the bottom. The science instruments are actually behind. This is the same case with Hubble, by the way. The science instruments are in a package behind the main mirror. So light from the target gets bounced around and actually ends up going into a hole in the center of the main mirror and into the science instruments. There are 4 of them. And importantly, 2 of them are cameras, as you might think of, and 2 of them are spectrometers. And what the spectrometer does is it takes the light and splits it up into, I would say, all the colors of the rainbow, all the colors of the red rainbow, right? All the different wavelengths. And those wavelengths are very diagnostic, as you'll see. So there are two cameras and two spectrometers, and curiously, or interestingly, they don't all point in the same place. They are taking off different parts of the focal plane, what we call a focal plane of the telescope. So like if you wanted to use all the instruments to study one object, you would have to study it with one instrument, then move it slightly so that the other one was pointing at it and so forth over time. Okay, so let's talk about this notion of spectrum. When we have a hot, very hot source, like the sun gives off essentially what we call a continuous spectrum. It gives off a broad range of wavelengths, basically based on how hot it is. The hotter the object, the brighter it gets, and the more that light gets shifted toward the blue end. Think of a hot coal in a fire, either a fireplace or a fire pit. When the fire is at its hottest, those coals are like a bright yellow orange. As you let the fire die down, the embers, the coals start to get dimmer. But if you think about it, they change color too. They go from yellow and orange through all shades of red. And then there comes a point when you can't really see them anymore, but you can feel them. You can still feel the heat coming off of them. And so that is, all of that is what we call a continuous spectrum. Now, a lot of things in nature don't emit a continuous spectrum. They emit what are called line spectrum. And a really good example is a neon bulb. Any neon bulb that you want. A fluorescent bulb, I'm sorry, I said neon, a fluorescent bulb. The fluorescent bulbs that are kind of ubiquitous, they give off white light, but they don't breathe it. What they're actually doing is giving off 2 or 3 specific wavelengths of light, a red one, a green one, and a blue one, so that when they're combined, our eyes are tricked into thinking that we're seeing white light, but we're really not. And so this line spectrum is very diagnostic because it tells us what the composition is of whatever is emitting that light. It's like a fingerprint. It's a radiation fingerprint. And so it's time for me to demonstrate again. No volunteers needed this time. So this is an atom. An atom consists of a nucleus of protons and neutrons surrounded by a cloud of electrons. This is an atom in a rest state. It's happy being there. It's just happy being there, right? Just like the gas in our atmosphere, happy to be there. If I add energy, right? Or maybe I add 2 bursts of energy. Now this atom is under stress. It's in what's called an excited state. It doesn't like being this way, just like the balloon doesn't like being this way. It would rather be in the rest state. But in order to get back into being a rest state, remember it took a certain amount of energy to inflate the balloon. If I want the balloon to deflate, I have to let the energy out. And so what happens is, in real life, there are different atoms absorb energy and become excited, and then release that energy at very specific wavelengths, go back to the ground state, and that is when we can tell what those atoms are from afar without actually being there. Here's another example of this with a little audio thrown in. I know you don't believe me, but you'll believe him because he's got a British accent.
Well, what else have we got which has got something peculiar about it? This one here has got a siren, which I've had for many years. That is noisy. I did it once. And a smaller one. Yes, kids love them.
So the point here is that if you're listening across a broad range of wavelengths, or looking, and you see certain emissions at certain frequencies, certain wavelengths, then you can tell what the source is, what the composition of the source is. For example, these are some examples of certain elements, certain atoms that give off really strong emission that we can pick up. Sodium is very, very common, very strong emissions in the yellow and orange. And you still see around what are called high pressure sodium streetlights. They have a kind of peachy color to them. And the reason they have that peachy color is they're only giving off 2 or 3 wavelengths, and you can see them right there at the top row. And so we use this technique to understand the composition of things that are really very far away. I talked about this a little bit. Not only can we tell their composition, but based on the distribution of the wavelengths, which ones are stronger, which one's weaker, we can tell the temperature of that object as well. Our sun, for example, has a temperature of about 5,000 Kelvin, 9,000 degrees Fahrenheit. There are stars that are much hotter and therefore bluer, or less hot, cooler, and therefore redder. All of this can be applied in terms of studying the spectra of the object on the sky, be it a planet, a cloud of gas, another star, a distant quasar or galaxy. And so these are some of the key targets that the Webb telescope was designed to study. Things very close, like extrasolar planets there at the right, and then things very, very far away. Seeing the light from 10 to 11 billion light years away that left those objects that long ago, that over time, because the universe has expanded, all of that light has been stretched to the infrared. It's the only way we're going to see these distant edges of the galaxy. I'm sorry, of our universe. So the launch took place on
Christmas
30
Day
2 years ago from French Guiana. That is a European rocket. It's not a NASA rocket. Elon Musk doesn't own that rocket. It's a European rocket
Standing by for terminal
5. It was the only rocket big enough and dependable enough to launch the Webb Space Telescope.
Attention pour les deux comptes
And here's the
finales.
countdown en français.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
UAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
NASA always has these corny packed sayings after something gets launched. So now I was mentioning that Webb had to be very far away from Earth to get as far away as possible, and where it ended up is a place called the Lagrange point 2, which is on the far side of the Earth from the sun, roughly 1 million miles away. It's actually these Lagrange points are kind of gravitational watering holes where the forces balance out, and the Webb telescope can remain there indefinitely, will remain there. It can never be visited by a spacecraft, at least as we envision it. And so it's far enough away from Earth and the Moon that those two are not a problem, and it's been working very well. On its way out there, it took several months to get out there. It had been set all folded up origami style. It unfolded much better. And this. There's the heat shield. Vibrators. You'll see it fan out in just a second. And then finally, the telescope itself unfolds, the structure unfolds, the mirrors snap into place, and it shows it's underway. It's been a very great success. Now, let's talk about the beginning of our universe. Going back to the time of the Big Bang, this really has been talk about cosmology, but there's some basics here. When the Big Bang happened, and all of the mass in the universe formed from nothing, and all of the space that we think of as the universe formed at that time, and time itself began at that time. It was a white-hot super plasma. There were no atoms. It was this big soup, superheated soup of electrons, protons, neutrons, and other subatomic particles. There were no atoms as we know it. And so as a consequence, there was no light as we know it. And even if something emitted a photon of light, it quickly got absorbed by all of the other stuff around it. So the universe is counterintuitively, in its very earliest stages, was super hot and completely dark. And so it had to be after the creation, where it had cooled enough for the first atoms to form, hydrogen, helium, and a little beryllium, to allow light to escape. And so there came a point, 380,000 years after the Big Bang, at which literally the universe lit up, and the first light appeared. And so we call that the era of recombination. It was 380,000 years after the Big Bang. And so it was only then that light could start to kick around. And so no matter how far back in time we look, how far to the edge, we can never look past that threshold. And in fact, when we look at, because everything has been expanding to longer wavelengths as we get farther away, that light is no longer light as we know it. It has been redshifted to microwave radiation. It's like a hum at radio wavelengths that permeates all of space. You can think of this as the echo of the Big Bang. This is a map of the whole sky, and as seen in microwave wavelengths, the little red and blue patches there are actually differences in temperature, and they represent differences in density, which is a really good thing. Because if the universe had remained completely homogeneous, nothing could have ever formed, nothing could have ever solidified. The fact that there's cold and hot spots means that there are different spots of density. And where there was more density, we got stars to form, galaxies to form, and so forth. So the goal here is to try to look as close back to that point in time as we can. Hubble tried. It got, the universe is 13.8 billion years old. Hubble took a couple of cracks at this and got back as far as initially to within 1 billion years of the Big Bang. And then, roughly 700 million years at its most extreme. But that still didn't reveal to us the very first stars, the very first galaxies. And that's the only takeaway you remember from this talk. That is the Webb telescope's job, is to see as far back in time as we can, to see those very earliest galaxies and stars. Okay, this kind of sets the
Galaxies
stage.
are like islands in the sea of space. They glow with the light of billions of suns. The Hubble telescope reveals nearby galaxies in exquisite detail. Galaxies like these fill the universe. Looking deep into space, we see an astonishing array of distant galaxies. It takes billions of years for their light to reach us. We see them not as they are, but as they once were. In one tiny region of the sky, Hubble finds some 30,000 galaxies. Within a single image, we can explore 10 billion years of cosmic history. Relatively nearby galaxies are fully formed, with complete spiral structures and smooth elliptical shapes. As we travel farther into space, we see galaxies as they were further back in time. These galaxies appear somewhat disheveled, their mature structures still developing. When the universe was young, newly formed galactic disks were ablaze with star formation. Beyond this point, clumps of stars that are beginning to form galaxies. we've seen but a handful of the billions of galaxies stretched across space and time. Just one small sliver of the universe, observed by Hubble.
Your nap time's over, right? Wake up. And so the point is that Hubble could only look back so far. And as great a job as it did is looking back, those very earliest galaxies, roughly 1 billion years after the Big Bang, were just little tiny smudges. You see the bottom one there, 1.1 billion years after the Big Bang. That's as good as we got with Hubble. And enter now the Webb telescope. Now, the Webb telescope actually used an interesting trick of light and gravity called a gravitational lens. And here's how it works. There's the Earth down at right? And if we look down into space, there are clumps of galaxies that form clusters of galaxies. And that represents a huge amount of mass all in one spot. Think of it as a giant stellar. And just like a magnifying glass, because Einstein told us that gravity, perturbations in space-time, could even bend light, that's what these galaxy clusters do. They bend the light of even more distant galaxies into a way that their light becomes concentrated. And we can see them thanks to the cluster that's in the way, whereas we wouldn't otherwise be able to. This is a Webb telescope image, a gravitationally lensed cluster of galaxies. The white thing that you see, well, there's one star there, 1 or 2 stars, you can see them with the spikes on them. All the other white things are galaxies in this cluster known as SMACS 0723. That's not why I'm showing you the picture. What I'm showing you is the little red arcs that you see. Those are galaxies much farther away that have been snapped into focus, in a sense, by virtue of the gravitational lensing that's taking place. Now, they're not very pretty, but we can still study them. We can study their light, we can study their shape, we can study their brightness. And these are all much more distant than what what the Hubble telescope was able to see. So these are the 2 cameras on, you'll see a couple of these comparisons, near images in wavelengths of infrared light that are closer to visible light, so they kind of look normal. They're false colored in any case. Beatty on the right there is even farther. So this is the fainter heat from these galaxies. And so consequently, when we take one of those pictures and we start picking it apart, these numbers here, Z, are an indication of how much redshift is taking place and therefore how far away. We are seeing objects that are within 1 billion years of the formation of the Big Bang. And you can see them there. One of the things that has been most astonishing by the Webb telescope so far is, you remember the little Hubble video, you know, the earliest galaxies were a little disheveled, we said. Very good. Well, guess what? With Webb, it was discovered that these very earliest galaxies not only were disheveled, they looked very mature. They looked a lot like closer the galaxies that we're familiar with in our neighborhood. You can see there they have good shapes. There's they're a spiral shape. That's another one that shows some of the shapes of these galaxies. Not only are they more mature in their appearance, but there are more of them than we ever imagined to be that soon after the Big Bang. The cosmologists saw this and went, because this is just not what they expected at all. And of course, we wouldn't have launched the Webb telescope if it was going to just confirm everything we already knew. So this is a big discovery from the Webb telescope, that the very early units in the very early universe, stars came together faster than we thought, galaxies came together faster than we thought, and more of them. We still need to figure out how that came to be. They were also more dusty. Dust is a funny word in this context. Dust means everything that isn't hydrogen and helium. In the normal course of things, like in space around us, stars that have, well, they have mostly hydrogen. That's the way stars work. but they also have all the other elements too, and they've gotten that way from countless generations of big stars exploding, creating elements as they did so, scattering their guts across interstellar space, and other stars that are in the process of forming and incorporating some of that material. And over time, then the amount of iron and carbon and other things becomes gradually enriched in successive generations of stars. Well, what we're finding is that in some of these very primordial galaxies, there is already carbon and other stuff. So again, the Webb telescope is just blowing out of the water our existing assumptions. Now, it has picked out one or two individual stars in these arcs, bright individual points of light that's smaller than a galaxy. Here's one that's Ardell, formed 900 million years after the Big Bang. So it's definitely doing its job there. And there are a lot of developments coming. You know, Webb has been up in space now for almost 2 years. Its science operations have been underway for 18 months. There are a lot of results. I update this talk practically every week to keep up with all the developments that are coming. So we're gonna leave the distant universe alone for a while. We're gonna start moving our way closer to let's talk about the Large Magellan Cloud, which is a kind of groupy dwarf galaxy that accompanies the Milky Way through space. And in there is a bright bright nebula called the Tarantula. And when we look, this is a regular image taken from Earth of that tarantula. It's a beautiful spot of place. There are bright stars in the middle that are causing the rest of the nebula to glow like a light bulb inside a black shade. And so when we zoom in on that with the Webb telescope, we get this beautiful ethereal, this is now an infrared image of that same area. And you can see the tortured wreaths of all the dust clouds in that area, all lit up by that one bright star there in the center. And this is the nature of nebulous. And we can, the interesting thing is that we can look at different wavelengths. And I'm not showing you that for the reason that you thought, because if you do, well, it is okay. Look, I mean, let's back up. Back up. I mean, that's just pretty, right? Just pretty. I mean, that's my mantra. Astronomy can be just beautiful. It doesn't have to be complicated. But the reason I'm showing you this is that now we can use the power of those spectroscopes that are on board the Webb to take a look at the nebula giving off the light and dissect the composition of it by looking at its spectrum. And we can tell that there's atomic oxygen, hydrogen, I'm sorry, molecular hydrogen and hydrocarbon dust. We can pick it apart. We're so very far away from it, 163,000 light years, and yet we can still make all those determinations. Coming a little bit closer, this is another beautiful nebula. Again, like the tarantula was in, can't see these here from Howard Point. I don't care how clear your skies are. You need to come with me to Chile or someplace in South America, and you can see these. This is a beautiful nebula. In the middle of that is a star called Eta Carinii that is right on the verge of exploding as a supernova. It may have already exploded as a supernova because it's 9,000 light years away. Maybe we just haven't gotten the word yet, right? It's a light travel. But it's a very unstable star. It became unstable, heavily unstable in the 1800s. But again, zooming in with a Webb telescope, this is like a shoreline, the orange there, right at the very top. In the S in years, you can see that spike coming down. There's a star just off the top of this that is illuminating this whole region. And the way this works is that when one of these stars forms, it like blasts out a shock wave that erodes the nebula around it. So you're seeing literally the sort of the shock front there of this expanding wave. And again, all the beautiful detail that's there. Webb has already taken its look at the Eagle Nebula, and we're now seeing through it and seeing more detail. It's actually a better version of this picture that we released a couple of weeks ago. I should probably substitute it. Coming a little bit closer now, this is what's called a planetary nebula. This is the fate of our sun. When our sun's about halfway through its lifetime, in another 4 billion years or so, like most adults, it's going to get old, cranky, and bloated. And eventually, it's going to go through this sort of cathartic racking itself with a concussion. It's like sneezing so hard that all your skin flies off. The outer layers of the sun our sun will fly off into space and create a bubble, a nebula around what's left of the sun. This happens quite a lot. It's the common of many stars of the sun's size. And so this is called the planetary nebula. This is what will happen to the sun. And there on the left, you see this are the two wavelengths from the Webb telescope. On the left, you can see that it looks like there's only one star in the middle there. But looking at longer wavelengths, you realize it's actually a binary. Interesting discovery. It doesn't really affect you can't really tell which of those stars sneezed and blew off its outer layers, but it was an interesting discovery. We're going to come a little bit closer. This is the Orion, beautiful constellation in our wintertime. If we could look at Orion with infrared eyes, it would be choked with dust from one end to the other. That is the nature of Orion. And in the Orion Nebula, which I think we're all pretty familiar with, there's a special concentration of this dust and gas. The four stars there in the middle of the trapezium are the four stars that have lit up the nebula and allow us to see it in all of its wreathy beauty. And what astronomers are finding now using Webb is that in this Orion Nebula, there are pairs of objects that are roughly the mass of Jupiter. They're not necessarily planets, but they're certainly not big enough to be stars, in pairs that are just kind of flying away without any star associated with them. Now, in the messy mix that happens when a solar system forms, there's a lot of collision and close calls and stuff like that. And I can imagine, a planet in an early solar system getting thrown out. Certainly that happened in our solar system. But two at one time, and two big ones at one time? This is one of those head-scratching things that no one understands quite yet. Oh, speaking of Jupiter, this is our planet Jupiter, the one that's gracing our skies, evening skies all winter. Seen in infrared light. We're looking at the heat coming from Jupiter. And it's because of that heat that we can make out its very, very thin ring. You see the great red spot down there at the lower right. This is a little closer view of it. The red spot is like it's a portal looking into the lower layers of Jupiter's atmosphere, where it's hotter. And so because it's hotter, because we have this sort of opening, it looks very bright because that's the infrared light coming up, infrared energy coming up from lower down. Similarly with Saturn, this is a beautiful picture of the Saturn system taken by the Webb telescope. You can see three of its moons there on the left. The rings look very bright. The planet itself looks dark. Why is that? Well, I'll tell you. Because the rings of Saturn are basically ice cubes. They are solid objects, and they reflect all wavelengths of light. Just like snow reflects, or a regular ice cube reflects everything that strikes it, reflects it back. However, Saturn, because it has a gaseous atmosphere, and because it has methane in that atmosphere, methane is an interesting gas. It's a very strong absorber of infrared light. And so the sunlight is shining on Saturn, but the methane is not allowing the infrared light to bounce back. So Saturn looks dark. There's a cautionary tale in this picture for Earth. You probably have heard that carbon dioxide is causing global warming. You might not have heard that methane is part of that. In fact, methane is a much more powerful greenhouse gas than carbon dioxide. And so, fortunate for us, there's very little methane in our atmosphere for the time being. There are vast tracts of frozen tundra up in, Siberia and northern Canada, where there's essentially big peat bogs that are frozen solid. If we ever get to the point on the warming of our planet where those massive tracts of permafrost thaw out, they will release their methane, and it will be game over from the standpoint of global warming. We really don't want that. Okay, So now the thing is that Webb is, I'm kind of getting to the end here. Webb was also designed to study the near universe and in particular the planets of other stars. We can see with great difficulty, we can pick out, we know that lots of stars have planets around them. But the problem is the stars are really bright and the planets, just like our planets, are shining by the reflected light of those stars. So they're very difficult to see. They're millions of times fainter than the stars themselves. We have to go bend over backwards, as these pictures show, to block out the star so that we can see maybe a few planets around. It's a very challenging observation. But within the last 20 years, astronomers have come up with a technique called transits, which allows them to find planets around other stars when otherwise it would be impossible to do so. And here's how that works. You're sitting on your porch, nice summer night, certainly warmer than tonight, and you're just admiring the evening sky and you got your porch light on, and suddenly you see this kind of fleeting shadow over your lap. And you look up, and there's this giant moth that's blown directly in front of the light bulb, casting a kind of momentary shadow on your lap. So you know the moth is there even without seeing it by virtue of that little shadow. It turns out that it doesn't matter whether that moth and that light bulb are 3 feet from you or 300 miles from you. The fraction of the lamp's light covered by the moth remains the same. And so we can use that technique called transit to detect when a planet passes in front of a star, some distant star. We can't see the planet. All we can see is that as we study the star's light, it takes a little dip once every 10 days, 100 days, whatever it might be. That's a planet orbit around that star that periodically it passes directly between us and the star. It blocks a little bit of the star from our view, and we detect it as a dip in the light of the star. And it's very diagnostic. It can tell if it's, it tells us whether we're talking about a little planet from a big star or a big planet from a small star. But importantly, I'm going to go back. Importantly, if that planet has an atmosphere, as the sun, and it's crossing in front of the star, as that star's light is streaming past the planet on its way, it didn't quite get covered by the planet, but it's skimming through the atmosphere on its way to us. The atmosphere of that planet imparts a fingerprint light from the star that's reaching us. Again, the spectrum here. And so we can tell when these transiting exoplanets, we can actually determine the composition using spectra, the composition of the atmosphere in that planet. A planet that we can't see, but we can tell what its atmosphere is made of. This is a simulated a spectrum, but this is a real Webb telescope spectrum of a real planet 1,100 light years away, and we can tell that there's water vapor in the atmosphere of that planet. Here's another one, again Webb telescope. This one's actually kind of controversial. We can see not water vapor this time, but methane, again, very strong absorber in the infrared, carbon dioxide, and something called dimethyl sulfide. You see it there near the middle? Dimethyl sulfide, as near as we can tell, can only be made by biological activity. And so we don't know of any inorganic way to make that gas. Now, that gas detection, it's on a margin of believability. Right? We don't know if it really is dimethyl sulfide, and if it's there, how much of it there is. But it could be telling us that this is a planet, and again, it's only 134 light years of planet. That could be hosting biological activity right now. So, pretty heady stuff. Again, we're only a year and a half or so into the studies with the Webb telescope of all these different aspects of the universe. Its projected function is for at least 10 or 15 years, and who knows what awaits us down the road. Thank you all very, very much. Stop the share here. There you go. All right.
There.
Yes.
So what are the latest thoughts as to why
there's so many galaxies that far back and how they form so big.
Right, Mario asks, for those listening on Zoom, what's the possible reason for having so many galaxies so far back? And it turns out that we think what's happening is actually the opposite of what you think might be happening. In our mind, you form a galaxy and then you've got this big, nice, rich concentration of gas and dust, and then you form stars in that galaxy. It might be the other way around. Because remember, the early universe is very dense. And so it might be that there was a furious, and continues to be, a furious formation of very massive stars very early in the universe, sooner than we expected that to happen. Sorry. And if they're all forming from one cloud, giant cloud of dust, then they will attract more, and it actually will be the seed for what ultimately becomes a galaxy. You might have heard just recently that there's a big controversy going on right now over how fast this process is taking place, and whether or not, this is important, whether or not these early galaxies are far more massive than any physical process we can imagine to make them that massive that soon. And it's a work in progress, but we think we get a way around it by having a whole bunch of these really intensely bright, very massive stars form early, and they kind of fake us out into thinking that their embryonic galaxy is far brighter and therefore far more massive than we think it is. But really, it's just these handful of super bright, supermassive stars forming early.
Can I just make one comment about the mirror?
Yes.
This is actually the most impressive thing about it.
Why don't you come up here so that people can hear you at home?
I just want to make the most impressive thing about the James Webb Telescope to me, the mirrors, is as a telescope maker, I know how hard it is to grind a mirror to perfection. We're another one right now, 12 inches, darn difficult. And the way you test it is to have it focus a light beam so that you can test millions of an inch accuracies. With James Webb being at about 10 degrees above absolute zero, they didn't have a room to test it that way. So they had to calculate the deformity of the mirror at room temperature so that when it cools down to that incredibly cold temperature, it snaps into the perfect shape. That to me is the most mind-boggling thing.
Yeah, worth every bit of the $10 billion it cost us to put it together. All right, I guess it's 25 billion. Go ahead.
Yes, there is no way that the age of the universe was underestimated and that actually the universe is older.
Yes, there is. His question is, based on these Webb observations, there is some sense that maybe we've underestimated the age of the universe, and it might be actually much older than we figured. Based on this notion, it's a notion called tired light. And that notion is as follows. Yes, the universe is expanding, and that's causing this redshift of infrared wavelengths. But somehow the physical nature of electromagnetic propagation is when you travel far enough, the light kind of gets tired and stretches to a longer wavelength. And so maybe this light has actually taken longer to reach us than we think, than the 13.8 billion years. That has been out as an idea, but nobody really believes it. There are reasons why. There are reasons to believe that the light that we're seeing, this tired light, would not be high in this. It's a little complicated even for me, so I'm not going to attempt to explain it. But you're right, it is out there that this notion that maybe the universe is twice the age that we think it is, because of this tired light phenomenon, and it's not supported universally. It's basically an idea without too many followers at this point. But thank you for bringing that up.
Was that a halt and ARP idea?
I'm sorry?
Is that a halt?
No, I don't. Well, I might have been. Maybe Bill Waller knows the answer to that. He doesn't. He's gonna take a pass. Any other questions here, and then we'll see if anybody, yes, go ahead.
Building a little off this question, I heard there's supermassive black holes that are being found like way too early in the universe for it to make sense. What do you have to say about that?
Right. Again, this is based on, so, hold on a second. Sorry.
There you
Our Milky Way, you wouldn't know it, but to look at it, but at the center of our Milky Way is a supermassive black hole. Right? Supermassive, it's millions of times the mass of the sun. And it turns out that pretty much every galaxy has a supermassive black hole in its center. Now, it turns out that the size of it, in terms of how much mass is in there, scales as the size of the galaxy. And so what is being observed is radiation from these supermassive black holes and these very distant galaxies that would lead us to believe, based on this relationship, that the galaxies themselves are not only are the galaxies big, but the supermassive black holes are larger than they could possibly grow. Right. Now, here's the thing. We know these supermassive black holes exist, but we don't know how they form. There are many kinds of black holes. There's only one kind of black hole that we actually have a really good grasp of how it forms, and that's called a stellar mass black hole. It's when a very massive star explodes as a supernova. Part of what's left behind collapses to form a black hole of, several, maybe up to 10 or 20 times the mass of our sun. We have evidence that these supermassive black holes form in virtually every galaxy, but we don't know how they got there. We don't know how they formed. And so you're absolutely right. That's one of the things that's out there. I did see that paper and I skimmed it, and I didn't understand it or didn't dig deep enough to really understand it. Again, my understanding is there's a way out to keep it from being contrary to physics as we know it. And I'm sorry I don't have a better answer for you than that, but you're absolutely right, and you get a gold star for like keeping up with the literature. Let's see, anybody online here, Zoom wise, you can use the little reactions down at the bottom to raise your hand or just wave at me. Most of you are camera shy, so okay, I like all your smiling faces. Thank you very much for that. Maybe one more here and then we'll break for time. Who's going to ask me the last killer question? Go ahead.
You were talking about I forget what I said. Talking about the planet extracting.
Yes.
How does that work?
I'm sorry, what extracting?
You were talking about
The expanding universe?
Yeah, expanding universe.
So why is it expanding? Or well, it's expanding because when the Big Bang happened, it's hard to imagine creating everything from nothing, but that's what happened. Right? We believe that all the mass in the universe, all these trillions and trillions of stellar masses of material came from this point singularity that itself had no mass, and then miraculous physics happened, and all of this mass started expanding. Now, once you create the mass, it doesn't all want to be in the same place, so it expands to, and space is formed with it. This is the part that I have a hard time grasping. The notion, it isn't that all of this happened and expanded into an existing empty room. There was no empty room. So the Big Bang created not only all the mass in our universe, but the three-dimensional spatial framework in which it all exists, plus time. And so that is a consequence of the formation of the Big Bang. It's just the way the physics works. Everything wants to run away from each other. And actually, the reason this Hubble, determining this Hubble constant, the expansion rate is so important is we needed to find out is the expansion rate slowing down such that someday it might all come back crashing together? And it's not going to do that. We now know that we have an open universe. But also, Hubble's studies of these very disparate supernovas, which they used to measure the expansion rate, led us to the conclusion that Einstein was right. That not only is the universe expanding, but that expansion is speeding up, counterintuitively. It's not slowing down, it's speeding up. And this is where this concept of dark energy, so think of it as anti-gravity, comes into play. Now, early in the universe, anti-gravity was as a dominant force as it's turning out to be now in the later stages. And so it's causing, not only is the expansion proceeding, but it's actually accelerating it.
I saw a recent paper that's from James Webb saying they looked at the cluster that we're in. I can't remember the name of it, but it's showing something that we don't know what the Hubble expansion rate actually would be. And
Oh, yeah. Right. So you're right. There is a big fight going on in cosmology right now over the Hubble constants. There are two ways to determine that. One is to take a look at something really distant, like a supernova, determine how far away it is and how fast it's moving away from us. That's one set of observations. Another set of observations is using this microwave energy, that sort of echo from the Big Bang, and measure it in such a way that it itself yields a number. Now, before we got very good at this, those two techniques yielded basically the same number. And as we've gotten better at it, using Webb telescope, the solutions are divergent, right? This is called the Great Crisis, you know, and there's no end in sight. And basically we've gotten to the point where the error bars between these two methods are sufficiently small that we know they are different. So there can't be two, right? One or the other of them has to be right. That means one or the other of those techniques has to be wrong. Stay tuned. Maybe then by this time next year we'll have the answer. Folks, thank you all very much for your attention.
Thank you, Kelly.
Thank you very much for this. It was wonderful. I actually had goosebumps.
Good, folks, great.
Me too.
All right, thanks for coming, everybody.
Thank you very much.
Drink
Have a
something.
Happy New Year.
Happy
Oh, listen.
holidays.
Our January meeting is always a planning meeting where we get together and we decide who our speakers are for the coming year. Which is a lot better than getting all nervous about it every month, trying to find somebody. People are welcome to come, but there's no entertainment other than watching us. Okay? You're welcome to come. There will be,
enough.
but there won't be any speaker at the January meeting.
Have a Happy New Year then.
Happy New
Merry
Year, everybody.
Christmas.
Merry Christmas, everyone.
Thank you, Kelly.
Thank you,
All right,
Michael.
see you guys.
Kelly,
Bye-bye.
nice job. Thank you.
Closing the doors.
Bye.
Hey,